The objective of this video is to explain the color coding scheme for digital images. So I wanted to start with a real quick review. Shakespeare's complete works have approximately 3.5 million characters, which is bigger in file size. Shakespeare's complete work stored in plain ASCII text, or a 4-minute song on MP3. How much bigger is one or the other? And the second one, this is a little trickier. Assume your internet connection can transmit 1 million bits per second. Approximately how long would it take you to download 1 terabyte of data? Here's a hint. First, figure out how many bits a terabyte is. Second, be prepared to wait a long time. That review is great before a lesson like this, so you can think in the context of bits and the scale of bits. So consider how color is represented on a computer, and imagine how it might be encoded in binary. Today you'll learn about the RGB color scheme and create your own images in an all-new version of the pixelation widget that allows you to use more than 1 bit per pixel to represent color information. After grappling with the prospect of possibly many bits just to represent a single pixel, students are shown how using hexadecimal allows us to represent many bits with fewer characters. So a major outcome of this lesson will also be the understanding of the relationship between hexadecimal, which is base 16, and binary, base 2, and how useful it is to use hex to represent groups of 4 bits. It's important to realize that using hex is not a form of data compression. It's simply a different view of the bits. So think right here, what is hexadecimal good for? The most common color representation scheme is RGB. Typically, this uses 24 bits, that is to say 3 bytes, with 8 bits each for red, green, and blue intensities. And one of the most common ways you see this color represented is in hexadecimal. Think right, share, what does RGB stand for, and how many bits are in each category? How many bits? So another important objective of this lesson is to understand how uncompressed image file sizes can become quite large. For example, even a relatively small image of 250 by 250 pixels is a total of 62,500 pixels, each requiring up to 3 bytes. That is to say 24 bits of color information. So resulting in a total of 1.5 million bits to store one image, that's quite a bit. Thus, interesting connections to compression can be made here, but note that lossy compression and image formats like JPEG are covered later. So, computer screens emit light. That should be no surprise to you. When you mix RGB colors, you're really mixing light together. It is illustrative to look at how you make black and white with paint versus light. Remember in a couple slides ago when I just said that we're mixing light together? Maybe you think back to your days in kindergarten where you mixed paint together and it was amazing to see what colors mixed to make other colors. Well, for light it's a little bit different. To make black with paint, you mix everything, right? Everything together. With light, to make black, you turn everything off. So you get rid of everything, kind of. To make white with paint, you don't use any paint, assuming the canvas is white. So you don't have to paint or do anything. But with light, turn on all the lights for a full spectrum of color, and you have white. What do you think about gray right here? How do you make gray? If you guessed, put everything in the middle, so the exact half of 255, don't forget the 0. So kind of divide 256 by 2 and you get the number you would need for each RGB value to give you gray. This can make mixing colors a little bizarre too. So I have a fun widget for us to use. With paint, mix full red and full blue to make purple. With light, when you mix full red and full blue, it makes pink. So go to this link right here, and I'm going to just leave this widget very open to you. There's no real assignment. Just go ahead and log in and play around with that thing and see what different colors you can come up with. you don't have to do the task that you're going to see there. That's for tomorrow, which is the second part when you click finished. So again, just play around and check things out. Okay, this is my serious Bitmoji. Anytime you see this, sit down, we need to talk. This is serious. I'm going to say something I think that is very important, so pay very close attention right here. It is important to note that hexadecimal numbers are used to aid humans in reading longer strings of bits, but they in no way change the underlying data being represented. Instead, they allow us to read 4 bits at a time rather than 1, and so allow us to more easily parse binary information. Just staring at a screen of 1s and 0s could be maddening. But if we're looking at hexadecimal numbers, everything kind of makes a little bit more sense. So it's not a compression tool. Hexadecimal is compressing nothing. It's just helping us humans understand the computer a little bit better. So as I wrap up here, just a note, megapixels, that is millions of pixels, are a standard figure of merit for digital cameras. If a camera captures too few pixels, it can't take good photographs. But no one should think that more pixels invariably yield a better image. If a digital camera has a low-quality lens, more pixels will simply produce a more precise representation of a blurry picture. Couple think ratios as we wrap up. How many bits or bytes are required to encode an image that is 25 pixels wide and 50 pixels tall if you encode it with 24 bits per pixel? The second one, think right share. Imagine that you have an image that is too dark or too bright. Describe how you would alter the RGB settings to brighten or darken it. Give an example. The correct answer for that first one is 30,024 bits. If you want it in bytes, I have it right there. But when I did this math problem, I jumped directly to bits. So here's one calculation for you to use. And to tell you the truth, when I first did the calculation, I came up with only 30,000 bits because I just times everything together. I did 25 times 50 times 24. If you want a slower approach, you could think that if it's 25 pixels wide and 50 pixels tall, and each pixel has 24 bits in it, you can do the same multiplication just the other way. However, the reason it's 30,024, I realized, was I totally forgot about the metadata. What does it say? How many bits are required to encode an image that is 25 pixels wide and pixels tall? You need metadata for the tall and wide part. So 25 times 50 gives us 1250. 1250 times 3. Remember, 3 times 8 is 24, so pay attention to bits versus bytes of RGB for each pixel is 3750 bytes of RGB data, so that's just the RGB data only. And then we add 3 bytes of metadata, so multiply by 8 for a number of bits of 30,024. So there's the bytes, there's the bits, don't confuse the two. And here we are at the DOL. How are images given color on a computer or smartphone? Don't forget the metadata.